In this video, we will be graphing logarithmic functions. First, just a little recap of transformations. So as a reminder, the a and the c outside of the function, they represent vertical transformations. So your a is your vertical stretch and compression. This multiplies all of the y values by a. So whatever you see is what you get. If the a value is 2, you are stretching because you are making the values bigger. If your a value is a third, you're compressing because you're making your values smaller. And if the a value is negative, you're also reflecting over the x-axis. The c value that is outside of the function attached by addition, you are adding this to your y values, and this causes your function to shift up or down depending on the sign. Inside the function surrounding the x are the horizontal transformations. So your k value is about your horizontal stretches and compressions, but thinking of opposite operations, when you see k, the actual multiplier is the reciprocal, so 1 over k, which means if your k value is 2, that's actually a compression because the multiplier is a half. If your k value is a fifth, that's actually a stretch because the multiplier is 5. And if your k value is negative, that results in a reflection over the y-axis because all of your x values would switch signs. And finally, the value that is added or subtracted to x inside the function is your right-left movement, the shift. Now remember, again, opposite operation. So if you see x plus 3, the opposite operation is subtraction. You are actually going to the left. If you see x minus 4, the opposite is adding 4. That's actually going to the right. Now, we've been graphing transformations one transformation at a time. We graph our base function, then apply the transformations. A shortcut is something called mapping rule. And that is where you take all of your original base function points, let's call them x and y, and apply the following mapping rule. Now, this mapping rule is not something that should be memorized. It is something about your transformations. So you'll see for your x value, 1 over kx. That is your k value multiplier, the reciprocal. So I'm going to multiply all of my x's by 1 over k. That will result in that stretch or compression. And then I add whatever my shift is. Now use the operation that actually corresponds to the type of shift you're doing. So if I'm trying to shift to the right 3, I'm going to add 3 to those x's because I want to move to the right. Then for the y's, I multiply my y's by a, because whatever you see for a, that's what we multiply y values by. And then we add c for that vertical shift, that up, down. Now this mapping rule is going to apply to every type of function we've seen that is being transformed. So you're more than welcome to use this mapping rule from now on. But we've never graphed log functions before, so let's get started. We're going to start with y equals log of 3x minus 10. Now remember, if you don't see a base, the base is automatically 10. Now your base function, the one that has not been transformed, is just y equals log of base 10 of x. Now, how are we going to graph this? When you see a logarithmic function, remember, you can convert it into its exponential form. So this can be converted as 10 to the power of y equals x. So when I create my table of values, I'm actually going to pick my y values for the first time ever probably, because then I can just do 10 to the power of that value, and then my x would be spit out. I'm going to start with -1. So that means to get my x value, I'm going to do 10 to the power of -1. Now that means I'm going to take the reciprocal of my base to turn that exponent positive. So that's actually 1 over 10 or 0.1. Now I'm going to pick 0 for y. 10 to the power of 0 is 1. Now I'll pick 1 for y. 10 to the power of 1 is 10. And finally, I'll pick 2. 10 to the power of 2 is 100. So again, I am picking my y's. Now this is what my base function would look like. Now I'm going to create the mapping rule so I can put all of these base function points into this mini little formula. Now before I do my mapping rule, I do like to think about my transformations. That way I'm not just mindlessly memorizing something. There's no a value here, it's just an invisible one, which isn't going to do anything. My k value is 3, which means I am horizontally compressing by a third. And then I'm going down 1. The horizontal affects my x's. And we said that it's a horizontal compression by a third. So all of my x values will get multiplied by a third. Now for my y's, there's no vertical stretch or compression. I'm just going down 1, so I have to take all of my y values and subtract 1 from them. And now I'm going to apply this to that base function table of values, starting with my first coordinate. The x value is 1 over 10, so I'm going to do a third times 1 over 10. That's 1 over 30. If you want to write that as a decimal, feel free to do so. For the y value, I have to take the y, which is -1, and subtract 1 from it. That's -2. Next coordinate. When x is 1, I'm going to do a third times 1. That's a third. When y is 0, 0 minus 1 is -1. Next coordinate. 10 times a third. Here we are, or 3.3 repeated. 1 minus 1 is 0. And last one, when x is 100, and we multiply that by a third, we get 100 over 3. And when y is 2, 2 minus 1 is 1. And here we go. Now we can plot our points. Now it might be useful to turn those fractions into decimals, but here we go. Our first coordinate that I'm going to plot is 1 over 30, which is 0.0333. So we're pretty much touching 0 here, comma, -2. So there's my point roughly. Then I have a third, comma, -1. So a third is 0.3 repeated. Here we are. 10 over 3 is 3.3 repeated, and that's comma 0. So there we are. And 100 over 3 is 33.333 repeated. That's not going to fit on our page. So now I'm going to connect my dots, and here we are. And remember, we are going to have an asymptote, and that asymptote in this case is right on our y-axis because there is no right-left movement. So the vertical asymptote is x equals 0. Now, do we have an interval of increase or decrease? Well, if I read this from left to right, I am always increasing from 0 to infinity. So from the asymptote onwards. When is this function positive? Well, right where the x-intercept is, onwards. And that x-intercept, we don't have to solve for it because it's already found in our table of values. So from 10 over 3 to infinity, we're positive, which means from the asymptote of 0 to that 10 over 3, we are negative. And for our end behaviors, I'm going to write as x approaches infinity, y also approaches infinity, slowly, slowly. And I'm not going to write as x approaches negative infinity because there's nothing there. I'm just going to write as x approaches my asymptote, so as x approaches 0 from the right, y approaches negative infinity. Those are appropriate end behaviors for this logarithmic function. And that's it. Let's try another one. So this next one is also a base 10. So the base function is log base 10 of x, which means when I write my base table of values, I'm doing that 10 to the power of y equals x again. So I'll just get that set up the exact same way as I did with the other one. And maybe this time I'll just go and write these as decimals. Okay, and now I can figure out my mapping rule. Now, before I do that, the same rule as with regular transformations apply, which is you have to factor out that k value to get the correct transformations and the correct mapping rule. So I'm going to factor out the negative, and here we are. So clearly I don't have any vertical transformations. There's no a or c value, so my y's are not changing. So I'm actually just going to go ahead and rewrite those because nothing's changing there. But for my x's, I have a reflection, which means all of my x's will get multiplied by -1. And then that x minus 2 is actually telling me that I'm going to go to the right 2. And if I'm going to the right 2, I have to add 2 to my x value. And now we can apply our mapping rule to our original x's. So -0.1 plus 2 is 1.9. -1 plus 2 is 1. -10 plus 2 is -8. And -100 plus 2 is -98. Now, of course, that last coordinate is kind of useless to us, but let's go ahead and plot the rest. At 1.9, we are at -1. So maybe something like that. At 1, we're at 0, and at -8, we're at 1. Now, something I'm just going to draw in before I connect my dots is my vertical asymptote. The vertical asymptote used to be on the y-axis, but because I'm going to the right 2, my asymptote will change as well. And that way, when I connect my dots, I have a guide that I cannot pass. And there's our function. Now this function, when we read it from left to right, is decreasing from -infinity all the way to our asymptote. The positive interval is from -infinity until that x-intercept of 1. And then we're negative from 1 until the asymptote. And behaviors, our function is only going to -infinity. So as x approaches -infinity, it is heading up slowly, so y approaches infinity. And then as x approaches our asymptote of 2, and we're approaching it from the left, y is going down forever. So y approaches -infinity. So 2 examples with our base function of log x with a base of 10. But of course, those bases can change, like in our next example. We're going to graph y equals 2 log base 2 of 2x minus 6 plus 1. Before I even think about transformations, I'm just going to write down my base function, which is y equals log x base 2. And the exponential form that's going to help me graph is 2 to the power of y equals x. So again, I'm picking my y values. I'm going to start from -1. And you know what? Because our base here is 2, I can actually go a little bit more to get more accuracy. So 2 to the power of -1 is 0.5. 2 to the power of 0 is 1. 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. Now let's think about our transformations. But before we do that, we have to, of course, factor out our k value, which is 2. And here we are. So in terms of vertical, I am vertically stretching by a factor of 2, and I'm going up 1, which means my y value has to be doubled to get that stretch. And after I'm stretched, I go up 1, so plus 1. For the horizontal, I am horizontally compressing by a factor of 1/2 because I have to take that reciprocal. So my x's are going to get multiplied by 1/2. And then I'm going to the right 3, opposite sign. So if I'm going to the right 3, I'm going to add 3. The actual transformation itself is what you use in your mapping rule. And now let's do that. We have 0.5 times a half, and then add 3 to it. That's 3.25. And then for our y, 2 times -1 plus 1 is -1. A half times 1 plus 3 is 3.5. 0 times 2 plus 1 is 1. Next x, a half times 2 is 1, plus 3 is 4. For the y, 2 times 1 is 2, plus 1 is 3. Next, 4 times a half is 2, plus 3 is 5. 2 times 2 is 4, plus 1 is 5. Last x, 8 times a half is 4, plus 3 is 7. And last y, 2 times 3 is 6, plus 1 is 7. And let's go ahead and plot that. 3.25, comma, -1, 3.5, comma, 1, 4, comma, 3, 5, comma, 5, and 7, 7. Now where would my vertical asymptote be? Well, the function moved to the right 3, so did the original asymptote. So it is at x equals 3. And now we can connect our dots to draw this function. Now we can't read off our x-intercept, we didn't solve for it, so we're just going to jump to our interval of increase, decrease. This function is increasing from the asymptote at 3 to infinity. Our end behaviors, as x approaches infinity, so does y. And for the asymptote, as x approaches 3 from the right, y goes down to -infinity. And our final example, y equals 2 times log base 3 of 3x plus 12 minus 2. So our base function is y equals log x with a base of 3. Which means we are going to use the exponential form, which is 3 to the power of y equals x. If you would like to pause the video here and write your base table of values, please do so. And here's what we should have. I'm going to pick my y values. 3 to the -1 is a third, and I am going to keep my fraction here. Otherwise, I lose my accuracy. 3 to the 0 is 1, 3 to the 1 is 3, and 3 to the power of 2 is 9. And we can put another one, 3 to the power of 3 is 27, just in case it will fit on our graph. Now, in terms of our mapping rule, of course, we are going to factor out our k value first. And we have a vertical stretch by a factor of 2, a horizontal compression by a factor of a third, left 4, down 2. So why don't you pause this video and try to write out the mapping rule for yourself and then come back to check your work. So your x value will get multiplied by a third for the horizontal compression, then subtract 4 for that left 4. And the y's will get doubled for the stretch and subtract 2 for the shift down. And now we can apply that mapping rule to our base coordinates. So a third times a third is 1/9. Subtract 4, you're going to have to get a common denominator here, or at this point you can write the decimal because we do need that decimal to graph. And then for the y, -1 times 2 is -2. Minus 2 is -4. Next, 1 times a third is a third. Subtract 4, -11/3, or the decimal equivalent, which is -3.6 repeated, I believe. Yes, it is. And then 2 times 0 is 0, minus 2 is -2. 3 times a third is 1, minus 4 is negative 3. 1 times 2 is 2, subtract 2 is 0. 9 times a third is 3, subtract 4 is negative 1. 2 times 2 is 4, subtract 2 is 2. And last one, 27 times a third is 9, and 9 subtract 4 is 5. 3 times 2 is 6, 6 minus 2 is 4. And now we can go ahead and plot these points. And 35 over 9 is 3.8 repeated, negative 3.8 repeated. So I'm going to start off by plotting that point. And then negative 3.6 repeated. And then negative 3, 0, negative 1, 2, and 5, 4. And where would my asymptote be? Well, we have to shift left 4 units. So the asymptote will shift as well to x equals negative 4. And now I can connect my dots. And this is an increasing function from the asymptote at negative 4 to infinity. My positive interval is from that x-intercept of negative 3 to infinity, and my negative is from the asymptote to the x-intercept. And our final end behaviors, as x approaches infinity, y is also approaching infinity. And as x approaches our asymptote from the right, y approaches negative infinity. And that's it for graphing logarithmic functions. Now, again, as a reminder, write your base function, convert it into exponential form, and because your exponent has the y, you get to pick your y's, and this little equation will spit out your x's. And with regards to your mapping rule, do not memorize it as a formula. You already know your transformations. So just use your transformation knowledge to logically think about what you're doing to x, what you're doing to y to get that mapping rule. Don't waste brain space on memorizing a mapping rule when you already know your transformations. And that's it for graphing logarithmic functions.